identify the compound. And generally, this is so predictable and so repeatable that once I've run a particular compound and a computer stores that spectrum's information, then it does it the same way every time after that. So I'll run that sample again 10 years later. The same peaks will be present with the same relative abundance. And so it's very stable. This is one of the techniques that can be introduced in a court of law, for example, without question. If the sample, the only question is, was the sample properly run? Because if you've got a good identification for, say, cocaine or something like that in court with mass spec, pretty much unchallenged. Now, here's what happens. I take my sample, this is a pretty simple sample. We got methane. I strike it with a high energy electron. The electron strikes it, knocks an electron loose, and gives me a radical cation as the product. Because I've lost an electron here, this thing is carrying a positive charge, and because one of the electrons now is unpaired, it's a radical. What normally happens now is this thing says, I don't want to be a radical cation, and it falls apart into radicals and cations. Okay, and that's the fragmentation pattern. So as soon as I've knocked an electron loose, then the thing begins to fall apart into what are the most stable possible fragments. And interestingly enough, those fragments, the stability associated with those fragments, correlates with what you already know. In other words, tertiary carbocations are more plentiful than secondary, more plentiful than primary. Tertiary radicals are more plentiful than secondary, and so forth. In other words, the general theory that you already know can be applied to what we expect to see in the mass spec. Now, there was a time when I was young, and this was a fairly new technique, where this took a little bit of operator knowledge. And you'd run the mass spec and say, oh, here's a methyl group coming off, or here's an isopropyl group coming off, and you could actually reason your way through the spectrum. You don't bother with that. The computer does all the work for us. And so we'll look at it from that perspective. Just recognize that this is the case. Here's Fa. I've knocked off an electron and I've produced the radical cation. In one case, this could pass all the way through the system and be detected. However, I could have a hydrogen radical and an ethyl cation, or I could have a methyl radical and a methyl radical and a methyl cation. All fragmentation patterns are possible. The ones that are most likely, the ones that we see, tend to be the ones that are most stable. And again, you know the principles that govern that. The only thing the mass spectrometer sees is the cations. Okay, so when this, for example, if this process happens, I've knocked an electron loose, and this thing has fallen into a methyl radical, or a methyl radical and a methyl cation. The only thing this one sees is the methyl cation. The radical is lost in the system. Here's how the system is designed. We have some sort of a sample introduction method, and there's a number of ways of doing this. There can be a port, where I open the chamber up, put my sample in there, and then I pump the system down with a high vacuum. And the sample then is vaporized, and as it moves into the system, as it vaporizes, it passes through a beam of high energy electrons. The electrons strike some of the molecules of the sample and knock electrons loose. Once that's happened, the thing begins to fall apart and fragment. Okay. Pretty much instantaneously. All of the charged particles that have a positive charge associated with them are attracted to some slits, and they have a charge. What would their charge be?
Of the material?
Negative. Like they can either be a screen or slits. And so I've got these cations that are forming here, and they'll be accelerated toward negative slits that will focus their beam. The wall of the slits will be negative, but a few of them will miss the wall and pass through. And what that does is it creates a very tightly focused beam of positively charged particles. And they're streaming down the chamber now. At this point, right here, I apply a powerful electromagnet. And positively charged and negatively charged things are affected by a magnetic field. So this beam of magnetically or magnetically influenced particles begins to bend under the influence of the magnetic field, and it bends more for light particles whose momentum is less, and less for heavy particles whose momentum is greater. And I can adjust the strength of the magnetic field so that a beam or a particle of a certain mass exactly hits the detector is bent exactly right to pass all the way through the chamber and strike the detector. And the instrument is finely calibrated so that as it scans the mass range, it says anything coming through right now has a mass of 212.7345. And it just scans through all of the ranges and picks up all of the peaks that are coming through. The more particles strike the detector, the bigger the peak in the mass spectrum. Okay, and so what I do, what this does is it sorts the particles by mass and by intensity, by how many peaks, how many particles strike the detector. Does that make sense? Essentially, it's a fragment sorter. And then I get a response out here. The normal mass spectrum would be intensity of peak, which means the number of particles striking, and mass down here. All right? Yeah.
So depending on what fragment you get, does that depend on the magnet?
Yeah, exactly. Notice that if I've got a heavy particle here that has a high mass, it will be bent by the magnet, but not enough that it will strike the wall of rust. The lighter particles will be bent, their path will be bent too much and they'll strike the inside wall. Only particles of exactly the right mass will make it all the way through the system and strike the detector.
And so it just does that like a few times to find out.
Yeah, it can zip through the mass range fairly quickly.
Okay.
And over the course of a few seconds, you can actually see the entire mass spectrum.
Is this like a big?
They vary. There are, the high resolution mass spectrometers tend to be a little larger, but low resolution, like the one we have at the other campus, is not very big. It's maybe about as big as our IR, so it's not that big.
How do you make like an electron beam? Is that
Um,
an expensive part of it?
And it's actually easier than you think. Classical old televisions were cathode rays, electrons. They just had a device in the back that was essentially a glowing wire and electromagnetically controlled collar that would focus a beam of electrons, and it was under electromagnetic control so that it would strike various places on the screen and light it up. And our eyes and our perception is so slow, we weren't seeing the individual electrons striking the screen, we were just seeing an image. And so it's pretty easy to create an electron beam. This thing requires a very heavy vacuum. Why would I want that chamber completely evacuated?
You'll strike other particles further.
Yeah, if I've got oxygen and nitrogen, and then these accelerating positively charged particles don't make it through the chamber, they strike oxygen molecules or water molecules or nitrogen molecules. So I have to pump this thing down excessively in order to have this work properly. So it's a high energy technique, or high vacuum technique. This is again a description of what we just talked about. Beam of electrons causes fragmentation and ionization. The ions are accelerated and pass through a magnetic field where they're sorted. By the varying of magnetic field strength, the spectrometer can sort and detect the abundance of each mass by how many ions are actually striking the detector. The curvature of the ion's path depends on its mass to charge ratio. This is why it sorts. And when we get a printout in the mass spectrometer, it looks something like this. And where this is really abundance, and this is mass to charge. And so I'll see something that looks like this. Where each of these represents a certain mass to charge. Interestingly, this thing can actually knock off 2 electrons, but it's a rare event. We assume that almost all of the mass to charge values are based on the loss of just 1 electron. But it is possible for a molecule passing through to get an electron knocked off and then be hit again and knocked twice. But the instruments, the signal from that rare event is so weak we generally don't put it. you understand what I'm talking about here?
Mhm.
You'll see, when you see some, here's a spectrum here. This is 2,4-dimethyl-pentane. Very often, we don't see what's called the molecular ion, because as it forms, it falls apart so quickly, it doesn't survive the mass spectrometer, it doesn't get through to the end. Once in a while, when we do see it, this is real useful, because this gives us the molar mass of the compound. And it's less an electron, but that's such a small amount, it's perfectly useful. This thing has a mass of 100. Notice it also has a fairly pronounced peak at 85. What might have happened there? Let's pretend like we're old school spectroscopists here. What would have a mass of 15 that would come off? Methyl. Carbon's 12, and 3 hydrogens make 15. So this would be one of these methyl groups coming off and leaving that positively charged fragment behind, which would be a secondary carbocation. Can you see that?
You're saying it's that molecule minus a methyl group, is the 85?
Yeah.
Okay.
One might also think an isopropyl cation could form. Here, 3 carbons, 3 hydrogens, and 1 hydrogen here. Right?
So it would be.
So 36 plus 43? Is there a peak at 43 there?
Okay.
Can you see that? That would happen again if I struck this thing with high energy electrons and the thing fell apart to give me an isopropyl carbocation. Recognize that the inverse is happening also. Wherever I'm creating a carbocation, I'm creating a radical that corresponds with it that doesn't get detected. Okay. I've got one at 41, probably due to the loss of a couple of hydrogens along with the radical. Okay, very, very common for that to happen as well. And our slides don't get into this kind of analysis, but in the old days we did. We'd sit and stare at it, we'd argue, and people would go out and get coffee so we could sit and fight about what this means. It's all done by computer. Now, I can take a gas chromatograph, and you've seen gas chromatographs before. They are gas-carried samples, where I put a sample in here, and there's a packing material that I use to separate my compounds, and the effluent from the gas chromatograph can be tied directly to a mass spectrometer. And what will happen is the samples, as they come out sequentially and been separated, they can be then analyzed by the mass spectrometer. And the combination of GC, gas chromatography, and mass spectrometry, MS, GCMS, is real powerful. Primary way to introduce a sample into the mass spectrometer is with a GC. Okay? And why would a GC be a good way to put a sample in?
You don't have to use much.
Puts an individual, it puts.
Yeah, you don't have to use very much. Number one, we got good sensitivity, and it separates. So if I've got a mixture, let's say that I wanted to know what was present in a competitor's sample of diet soft drink. I could shoot it in there, and it separates each of the components in the column, and then it tells me what they are as they come out. Pretty darn powerful. And if I could put a GC detector here that's not destructive in front of this, and I can actually quantitate. And I can say, oh, well, this is Diet Coke, it's got so many milligrams of caffeine, it's got so many milligrams of whatever. And I mean, in one fell swoop here, I can analyze samples like that. Really powerful. Right? So the coupling of the GC to the mass spec is really useful. Now, if I do high resolution mass spectrometry, usually bigger magnets, more sophisticated controls and so forth, I can measure accurately to 1 part in 20,000 in terms of masses, which is pretty remarkable. So if we had a molecule that we know had a mass of about 44 and ran it in the mass spectrometer and found a mass of 44.029, we could identify it just by its molar mass. Notice that if I take various combinations